Students, today we are going to study refraction through a prism. A prism is the portion of transparent refracting medium bound by two plane surfaces meeting each other along a straight edge. Here you see A, B, C is a glass prism where BC is base of the prism, AB and AC, they are refracting surfaces of the prism, and here it is angle of prism A is angle of prism, and at this edge, if you see a glass prism, you will see there will be two refracting surfaces, base of the prism and uppermost is called refracting edge. Here you see A, B, C. ABC is a glass prism. Here PQ is incident ray which is passing through a glass prism. So we have PQ incident ray, QR refracted ray and RS emergent ray. Now you see, we know that when a ray of light passes from rarer to denser medium, the ray of light bends towards the normal. Here you see NO is first normal, N-O is second normal. When PQ passes through glass prism, the ray bends towards the normal, and after passing through denser medium to rarer medium, the ray of light moves away from the normal. Then we have PQ incident ray, QR refracted ray and RS emergent ray. RS emergent ray. Now you see angle PQN. It is angle of incidence represented by angle I. PQN. It is represented by I. Angle of incidence. SR N dash, it is angle of emergence represented by E, small e. Angle R Q O, it is angle of refraction at surface AB, at this surface AB. That's why it is represented by R1. Angle QRO, it is another angle of refraction at face AC, at this face AC, and it is represented by R2. Now we extend this incident ray PQ and SR emergent ray. So they meet at a point T. Now here you see KTS. KTS. It is called angle of deviation and is represented by delta. Delta is angle of deviation. It is angle KTS. Now, since TQO, since T, this point, T QO is equal to angle of incidence, angle I, and angle RQO is R1. We have angle TQR. Now you see angle TQR is equal to angle I minus R1. Also TRO is equal to angle of emergence E, and QRO is R2, angle of refraction at face AC, it is R2. Therefore, angle TRQ is equal to E minus R2. Now, in triangle TQR, in this smaller triangle TQR, QT has been produced outwards. See, QT, this line QT has been produced outwards. Therefore, the exterior angle delta should be equal to the sum of the interior opposite angles. That is, delta is equal to, see, delta is equal to angle TQR, angle TQR plus angle TRQ, angle TRQ. It is equal to delta, this angle of deviation delta is equal to I minus R, I minus R1 plus E minus R2. See, from where we are getting these values? Since angle TQR is I minus R1, and angle TRQ is equal to E minus R2. Substituting the values, we get del is equal to I minus R1 plus E minus R2. Simplifying it, we can write del is equal to I plus E minus R1 plus R2. Put it equation number 1. Put it equation number 1. In triangle QRO. See, in this triangle QRO, the sum of these angles, three angles, is equal to 180 degree. Therefore, R1 plus R2 plus angle QOR, this angle, R1 plus R2 plus this angle, it is written R1 plus R2 plus angle QOR is equal to 180 degree. Put it equation number 2. Now we consider one quadrilateral. See, in quadrilateral AQOR, in this quadrilateral, each of the angles AQOR angle AQO and ARO is 90 degree. Since the sum of the four angles of a quadrilateral is 4 right angles, the sum of the remaining two angles should be 180 degree. That is this angle of prism A plus angle QOR. This angle A plus angle QOR, this angle is equal to 180 degree. Put it equation number 3. Now see, from equations 2 and 3, from equations 2, second equation, that is R1 plus R2 plus angle QOR is equal to 180 degree and angle A plus QOR is equal to 180 degree. So from these two equations we can write R1 plus R2 is equal to A. Now put it equation number 4. Now see, consider equation 1. See, in equation 1, in this equation, substituting for R1 plus R2 is equal to A, for this value R1 plus R2 is equal to A, we have del or delta is equal to I plus E minus A. For R1 plus R2 we can write A. So from this equation, del is equal to I plus E minus A, we can write del plus A is equal to I plus E. Here del is angle of deviation, this angle, and A, angle of prism. Summation of these two is equal to I is angle of incidence, plus E is angle of emergence. Now see, put it equation number 5. Thus, when a ray of light PQ, when a ray passes through a glass prism, see, a glass prism, ABC is a glass prism. When a ray passes through a glass prism, the sum of angle of deviation and angle of prism is equal to sum of angle of incidence plus angle of emergence. Now this equation 5 shows refraction of light through a glass prism. Now to prove that mu is equal to sine of A plus del m upon 2 divided by sine A upon 2, to prove it, now you see, the deviation produced in the path of a ray of light by a prism depends on, number 1, angle of prism, second, material of the prism, third one, the angle of incidence. If the angle of incidence is increased gradually, the angle of deviation first decreases, attains a minimum value, that is del m, minimum deviation, and then again start increasing. See the graph. See this graph. Graph is plotted between angle of deviation on y-axis and angle of incidence on x-axis. Okay, in this case we get this type of graph. First you see in decreasing order, after reaching this point again increases, the curve increases. When angle of deviation is minimum, the prism is said to be placed in the minimum deviation position. A prism can deviate the incident ray through the same angle delta for two different values I1 and I2. I1 and I2 of the angle of incidence. I1 and I2 are angles of incidence, but when it is placed in minimum deviation position, there is only one angle of incidence corresponding to the angle of minimum deviation. In other words, there is only one angle of incidence for which the angle of deviation is minimum. It can be proved that when the prism is placed in minimum deviation position, the prism lies symmetrically with respect to incident ray and the emergent ray. That is, the angle of incidence is equal to the angle of emergence. E is equal to I. Obviously, when the prism is placed in minimum deviation position, the angle of refraction at the first phase and then at the second phase are also equal, and as a result, the refracted ray passes parallel to the base of the prism. Therefore, when del is equal to del m, that is, in minimum deviation position, angle E is equal to angle I, and R1 is equal to R2 is equal to R, say. Now, setting R1 is equal to R2 is equal to R in the equation 4, previous equation, in case of refraction through a prism, you see equation 4, if we substitute R1 is equal to R2 is equal to R, we get R plus R is equal to A, or 2R is equal to A, or we have R is equal to A by 2, A upon 2, half of A, half of angle of prism. Also setting del is equal to del m, angle of deviation is equal to minimum deviation, and E is equal to I in equation 5. In previous case, equation 5, that was the result of refraction through a prism. In that equation, if we substitute del is equal to del m and E is equal to I, we have A plus del m is equal to I plus I, or I is equal to angle of incidence, I is equal to A plus del m upon 2. We know that the refractive index of material of the prism mu is refractive index, mu is equal to sin I upon sin R from Snell's law. Substituting the values, we get mu is equal to sine of A plus del m upon 2 divided by sine A upon 2. See, here we are getting R is equal to A upon 2, A divided by 2. So, for sine R, we substitute sine of A divided by 2, half of A, and I is equal to A plus del m upon 2. So, for sine I, we write sine A plus del m upon 2. Now, we proved the relation, we derived the relation for refractive index, or you see it is related with refractive index is related with angle of prism and minimum deviation. Now we have proved this